Okay, we're going to go through our first section in Chapter 4 today, which is about, Chapter 4 itself is about trigonometry. It's our first step into trigonometry in this course, and we're going to be dealing with trig and trig functions, trig graphs, and then applications of trigonometric functions for about the next half of this course. So it's a pretty important step into where we're headed. Um, as I go through this, I'm going to go through it as I would with a class, with kind of the warm up that we do. You have different notes and supplements that you were given in class. And I'm going to try to go in the same order that we would in class, so that you're getting the same thing that people would as if they were in class. So the first thing that we normally start with, let me just pull this up here, so you can see what we're dealing with. You have two different things that you should have picked up for class today. The first is a sheet that says 4.1 Notes Supplement, which is really some old worksheets that I have with basically what comes down to lots of nice examples on them. So we're going to be using some of those examples. The second thing that you have is actually let's see here, is something that actually says 4.1 Notes. Actually, it's a packet that has the first couple sections of notes on it, 4.1 and 4.2. We're going to start with the supplement that has these problems to start with. Gives you some radian measures and asks you to sketch the angle without converting it to degrees. So normally I give this to classes, and just to find out what they remember from Algebra 2, I ask them to sketch these angles. So we're going to go through these together. I'll give you some hints along the way. Sketching angles that are in radian measures. So the first hint I'm going to give you as you look at these is that when we're talking about radians and we're talking about angles, we have an angle whose initial side is on the x-axis, and as we open up positively, it opens counterclockwise. And then what we have is what is called the terminal side of the angle. So this would be the angle right there. We use theta to represent an angle, just like any variable. We usually use theta for an unknown angle. So we have what's called an initial side and a terminal side. Now, when we are drawing in radians, it's important to remember some specific radian measures. We call these the quadrantal angles. So this would be 0 radians. And if we opened all the way around like a circle, well, a circle has 2 pi radians in it since the circumference is 2 pi r. Okay, so 2 pi is what would be all the way around. So 0 and 2 pi are really coterminal angles. They share the same angle, the same terminal side there. If we opened up only halfway, that would be 1 pi. If we opened up 90 degrees, that would be pi over 2, or half of a pi. And between pi and 2 pi would be 3 pi over 2. Those are the 4 quadrantal angles: 0, pi over 2, pi, and 3 pi over 2. And then 2 pi is if you went all the way around and landed at 0 again. So when we have an angle like 8 pi over 5, the first thing I want to think about is what a full revolution would be. Okay, so this would be 0 radians. And if we went all the way around, that would be 2 pi. Well, let's start by going halfway around, right here. In terms of this denominator, we know that this is pi here. But since we have it over 5, we know that this is equivalent to 5 pi over 5. Okay, obviously that would simplify to pi, which is what we know that radian measure is. But I'm trying to think of in terms of that denominator right there. So halfway to that point would be 2.5 pi over 5. And all the way around would be 10 pi over 5, which is equivalent to 2 pi. And then between 5 and 10 would be 7.5 pi over 5, or you could add these two to get that numerator there. Okay, now I know it's not great to have the decimals in in a fraction there, but we're just trying to get an idea of where this 8 pi over 5 would be. And now that we have this marked here as 7.5 pi over 5, we have a pretty good idea that 8 pi over 5, there's my initial side, would open up to about right there. It doesn't have to be perfect, this is just a sketch. But that would be 8 pi over 5. If you remember from Algebra 2, we're always interested in this angle to the nearest x-axis. It's called the reference angle. And in this case, that reference angle would be what we have left to go to the 10 pi over 5, which would be 2.5 pi. Let this zoom in a little bit here so I can write a little bit nicer. Our reference angle here, the angle back to the nearest x-axis would be 2.5 pi over 5. Okay, now they're not even asking for us that here, but I'm just trying to remind you of some of the things that we learned in Algebra 2. All right, the next angle measure is pi over 6. Pi over 6 is actually one of our important angles that we deal with quite a bit. Pi over 6, since this would be 6 pi over 6, and this would be half of that, which is 3 pi over 6, or pi over 2. I'll just leave it in terms of pi over 6 right now. This is 3 pi over 6. 1 pi over 6 would be 1/3 of that way, right there. Well, 1/3 of 90 is 30 degrees, so hopefully remember that pi over 6 is the same thing as 30 degrees. And I know it says without converting to degrees, but this is one that's pretty important that you remember. Pi over 6 and 30 degrees are equivalent. It's like saying 12 inches equals 1 foot. All right, so here is pi over 6. 13 pi over 9. Here would be 9 pi over 9. This would be 4.5 pi over 9, which would mean that this is 13.5 pi over 9. So 13 pi over 9 would be about right there. Okay, I'll draw my initial side there too. Okay, so there's 13 pi over 9 right there. 13 pi over 9. That's a pi symbol. Okay. 3 pi over 2. That's actually one of those quadrantals that we saw in the very beginning. 3 pi over 2 is right there. All right, this is where things get weird because there's no pi anymore. That's okay. Remember, pi is 3.14. So this is 3.14 right there, approximately. This is 0 or 6.28. Half of 3.14 is 1.57. So I've just written pi here, pi over 2 here. I've just approximated it to help us figure out where 5.6 is. If we add these two things together, we can easily figure out what is equivalent to 3 pi over 2, 4.71. So 5.6 is somewhere between 4.7 and 6.28. It's going to be right about in here. And for our sketch, that's good enough. 1.3, if we use the values that we had here, 1.3, we know 1.57 is the same as that pi over 2, so 1.3 is going to be somewhere in this area right here. So there's my initial and my terminal. There's 1.3. Okay, let's go back and look at the reference angle of a few more of these. We talked about that right here, but let's look at some of these other ones too. The reference angle in this problem, going back to the nearest x-axis, the reference angle is pi over 6. So anything that's in the first quadrant is going to have itself as its reference angle because you're going to go back to that x-axis. All right. In example C here, that value right there, the difference between 9 pi over 9 and this 13 pi over 9, that's 4 pi over 9. We don't have a reference angle in D because it's a quadrantal angle. In E, we know that this angle would be the difference between 6.28 and 5.6 there. So the reference angle is going to be whatever 6.28 minus 5.6 is, which is approximately 0.68. Now, these are all radian measures. Normally, if we have the pi symbol, we assume it's in radian measures. I don't have any pi here, so I'm going to write the word radian just to solidify that fact. And like we said in part C here, anything that's in the first quadrant, I'm sorry, not part C, in B, anything that's in the first quadrant is its own reference angle. So our reference angle here, back to that x-axis, is just going to be 1.3. Now what we're going to do is focus our attention on the actual 4.1 notes packet that you got. So you put that supplement packet away and actually pull out the notes and actually go into some more of the things now that we just talked about in a little bit more depth. What the definition of a radius is, which is the angle formed when you take the measure of the radius and take that same measure and you bend it along the circle there. That angle that's formed is 1 radian. Okay, so that's where the idea of a radian comes from. That theta here would be 1 radian because this measure, which is the radius, is the same as this measure here that's kind of curved along the circle. That's also the distance r. That's what 1 radian is. All right. Then we talk about standard position. That's where they talk about terminal side and the initial side, that I mentioned on the problems before. And then we move into reference angles. Reference angles is the acute angle between, sorry about that, the acute angle between the terminal side of an angle and the x-axis. Okay, so some examples of reference angles and where they become useful to us, we'll just do up here, because we have some room. Okay, if your angle, if theta is 7 pi over 6, right, if we were going to look at that angle, 7 pi over 6, well, 6 pi over 6 is the same as pi. So 7 pi over 6 would be just past that by 1 pi over 6. So here's 7 pi over 6 right here. Okay? There's 7 pi over 6. The reference angle here is the angle back to the x-axis, which is how far we went past the x-axis to get to 7 pi over 6, which is pi over 6. That's our reference angle there. If we had the angle 5 pi over 6, here's my initial side. Okay, now again, here's pi. That's 6 pi over 6. Okay, and if you want to write it like that, you can. 6 pi over 6. That means that 5 pi over 6, I'm going to leave it as pi. That means 5 pi over 6 is going to be just short of that by 1 pi over 6. So here's 5 pi over 6. And our reference angle again, I'll put that over here. Here's our reference angle. Our reference angle again is that same value, that pi over 6. And what we're going to see in the future is that the reason why these reference angles are so important is because these two angles, 7 pi over 6 and 5 pi over 6, will have almost the same 6 trig functions, sine, cosine, tangent, and their reciprocals. The same 6 trig functions as their reference angle, pi over 6. And you'll know what the trig functions of pi over 6 are because you'll have them memorized. So you'll be able to tell what these trig functions are very quickly All we'll have to do is figure out if they're positive or negative. All right, so then we have a few more where we're drawing angles that are in radian measure. So we have pi over 2 here, pi over 2. Here's my initial side, pi over 2 is right there. So I'll just draw it opening up like that. There's pi over 2. Okay, there's no reference angle there. Okay. One thing to remember about reference angles, I'm going to put this right here. We usually use theta prime to represent a reference angle. They're always positive. They're always acute. They're always back to the x-axis. All right, 11 pi over 6. Let's see where that is. So we're thinking in terms of that denominator of 6. So again, this is 6 pi over 6. We have 3 pi over 6 right here, which we know is pi over 2. This is 0 or 12 pi over 6. And then this, our 3 pi over 2 angle right here. Again, if you add the 3 pi and the 6 pi, you get 9 pi over 6. Adding these two together is a quick way to figure out what that numerator is right there. So 11 pi over 6. Well, the best thing to use here is that 12 pi over 6. 11 pi over 6 is going to be almost all the way around, but we got to stop short. How far short do we have to stop? Well, we have to stop. Let me draw my initial side on there. Okay, so there's the angle 11 pi over 6 that I just drew right there in red. Its reference angle is that angle back to the x-axis, or to the nearest x-axis, which would be this angle right here. It's always positive, it's always acute. Well, that, from the 11 pi over 6 to the 12 pi over 6, would be pi over 6. Four pi over 3. Okay, in terms of pi over 3, or in terms of a denominator of 3, this is 3 pi over 3. This would be 1.5 pi over 3. Not that that's really going to help us. And then this would be 4.5 pi over 3. These really aren't necessary for this problem, to be honest with you. I'm going to get rid of them. Because once you know that this is 3 pi over 3, that should be good enough. 4 pi over 3 is going to be past that. How far past that? Well, it's going to be pi over 3 past it. So I'm going to open up. This is 3 pi over 3. I want to go 4 pi over 3. So that's going to be right there. Okay. And our reference angle, here's 4 pi over 3. Our reference angle, it helps when we think about this because we've been past it by 1 pi over 3. So our reference angle here is pi over 3. Before we said that pi over 6 was 30 degrees. Well, pi over 3 is double that. 1/3 is double 1/6. So pi over 3 is 60 degrees. Okay, now while we don't want you going back and forth between degrees and radians, I think it's good to get that in your head so that you kind of know how big to make this angle right there. If you know that it's 60 degrees, you know that you need to open up about 2/3 of the way between our two axes right there. All right, 2.9, we got one of those decimals again with no pi. So know that this is 3.14 there, right? So 2.9, just go right about there. There's 2.9, put my initial side on there too. 2.9 radians. Okay, but here's where a little math's got to come in. Our reference angle would be that angle right there. So that would be the difference between 3.14, or pi, and the 2.9. So our reference angle is going to be pi minus the 2.9. So the reference angle is about 0.2416. clear this off here. So we're just taking second pi is right there above the caret symbol, minus 2.9. That's where we're getting the 2.146 from. All right, on the next page, they talk about converting from degrees to radians. So we need some conversion factors here. If we're going from radians to degrees, okay, we need to know a good conversion. Well, we talked before about how going all the way around a circle is 2 pi. Okay, so in other words, 360 degrees is 2 pi. Well, a simpler way would be to divide those by 2. 180 degrees, hold on here. We know that, I'm just going to write this up here, 180 degrees equals pi. That's what we're going to use for our conversion factors. So from radians to degrees, we want to multiply by 180 degrees over pi. That'll cancel the radians out and put us into degrees. If we want to go from degrees to radians, then we want to multiply by the reciprocal of that. We want to put the degrees in the denominator so they cancel out, and put the pi radians up in the numerator. Okay, and really our unit is radians, so I'll put that there for right now. Degrees, obviously we use a degree symbol. In these problems, I think it's a good idea that you do, like in this problem here, we're going to go to radians, that we have radians in our final answer. In our normal working with radians and such, notice here, like I didn't bother writing radians in the sketching and things, but I think in these problems, since that's specifically what we're trying to do, we'll put the word radians in there. So here we have 200 degrees. We want to multiply that by, since we're going from degrees to radians, pi over 180. Okay, you can use, I know our, in science classes we use kind of this sort of thing here. We say it's 200 degrees, and we put 180 down here, and pi radians up there. Okay, I'm fine with you doing that. Otherwise, in the past, I've just used a conversion factor, like a fraction, and said that either way, you're doing the same thing. Okay, when we start doing more complex conversions, I end up using this sort of thing like you'll see in your science classes. All right, so what we do here is we simplify. Well, the degrees cancel out. That was the whole reason for putting that in the denominator. And now we just are simplifying 200 and 180. Well, we can get rid of that multiple of 10 and just focus on the 20 and the 18. Between 2018, let me just throw this out there right now. So here's where we're sitting right now. 20 pi over 18 radians, but we can simplify that because 2 goes into both of those. So our final answer is 10 pi over 9 radians. Now we're going to go from radians to degrees. So I know I have 7 pi over 8 radians. So I'm just going to say, put the 8 down here. 7 pi over 8. Put my radians up there. I'm going to multiply this by 180 degrees over pi. Pi's cancel out. Okay, and really this is in radians too, so the radians cancel out. And we have 7/8 times 180. Okay, and we're going to be in degrees, which is what we want to be in. We can simplify between the 180 and the 8. 4 goes into both of those. 4 goes into 8 2 times, and 4 goes into 180. If you divide 180 by 2 twice, divided by 2 once is 90. Divided by 2 again is 45. So we have 45 degrees there. So we have 7 times 45 in my numerator over 2. 7 times 45 divided by 2. 157.5 degrees. All right, we're going to continue on in our notes here and look at arc length. And even though they don't bring it up, we're also going to talk about area of the sector as well. So when we're looking at a circle, okay, we have center of the circle right here. This would be the radius. We're going to open it up some angle measure, theta, okay? This is arc length right here, okay? And arc length we call S, okay? Arc length is really easy to find. If you know the radius and if you know the angle, the central angle, you simply take the radius times the central angle, okay? So why is this formula so simple? Well, it's so simple because theta must be in radians. That's one reason why we use radians, because it makes this formula and the area formula for that sector so much easier, okay? Now, if we wanted to find the area of that sector, if we wanted to know what that area was right there, which is a portion of the entire area of the circle, that would be 1/2 r squared times theta. But again, these two measures have to be in radians. Whatever that central angle is must be in radians. So if you look at A here, it says find the length of the arc. We're also going to find the area of the sector. Okay, so we have arc length is equal to the radius, which is 4, times central angle, 5 pi over 6. It'll give us the arc length. Okay. Arc length is going to be in the same units that our radius is in, so it's going to be in centimeters here when we're done. I could simplify between the 4 and the 6, 2 and 3. And so what we end up getting is 2 times 5, or 10 pi over 3 centimeters. That's the area of that arc. Okay, so, if we use that diagram right there, if that central angle was 5 pi over 6, and if that radius was 4, then that measure S would be 10 pi over 3 centimeters. The area of that kind of slice of the pie there would be 1/2 times the radius squared times that central angle, 5 pi over 6. So, however you want to simplify this, if you want to call it 8 times 5 pi over 6, and then between the 8 and the 6, we have 4 and 3, so we have 20 pi over 3 square centimeters. All right, this one here, we're just going to do the arc length here, just to speed things up a little bit. But the important thing is we need to turn that into radians first, not in degrees. So we've got conversion time here, 125 degrees. I've got pi radians over 180 degrees. And this is going to simplify to, let's see, 5 goes into both of those, 25 and 36 times. So we have theta is 25 pi over 36 radians. Okay, so now we can use that measure in our formula. So the arc length is going to be the radius times theta. The radius is 1.5 millimeters. I'm going to turn that into 3/2. Okay, 3/2 times 25 pi over 36, and then we just do some simplifying here. We're going to get 25 pi over 24. Same units for arc length, millimeters. Okay, the next thing we're going to look at here, sticking in the notes packet, is angular and linear motion. and angular speed. Okay, angular speed is how fast something is spinning. Linear speed, you're familiar with that. That's how fast something is traveling in one direction. We're going to turn that into angular speed with conversion factors. So some important things to know. If you read example 4 here, we're given that the turntable rotates at 50 revolutions per minute, and they want to know the angular speed. Doesn't sound like you're given enough information, but the important thing to know is there are 2 pi radians in 1 revolution. Okay, and then another one here, since it says 50 revolutions per minute, and then they want to know per second, we also need to know that there are 60 seconds in 1 minute. Okay, but I think we're okay with that one. This is the one that we need to make sure that we understand. Okay, so here's what we're starting with. We have 50 revolutions in 1 minute. All right. Actually, I'm going to change this up a little bit, because I think in your science class, I'm hearing people right. If we're going to be converting two things, because we're converting both the revolutions into radians, and we're going to turn the minutes into seconds, that we go out in two different directions. So we kind of put our starting value in the middle, and then on the left I'm going to convert the radians, or the revolutions, to radians. So I know that 1 revolution is equal to 2 pi radians. And then look at what happens. Revolutions cancel out. So right now, if we multiply across, we'd be in radians per minute. Okay, we don't want radians per minute, we want radians per second. So now we need to convert our minutes to seconds. So 1 minute, I'm going to put that in the numerator so that they cancel out, is equal to 60 seconds. So now I'm going to get these to cancel out. And what I'm left with, lo and behold, are radians and seconds. Radians per second, which is what I want. So now we just need to do some simplifying here. I see a common multiple of 10 right there that we can just cancel out. And it looks like all we have left out in the denominator now is 6. And actually, we can simplify between that 6 and that 2 over there. 1 and 3. So as I multiply across now, it looks like we have only the 5 radians. 5 radians. Oops, sorry. I missed a pretty crucial thing here. 5 pi radians per 1 times 3 seconds. Okay, but they want radians per second. So we know that this would be 5 pi over 3 radians per second. Or we can give an approximation too and actually take 5 pi divided by 3. Get approximately, what was it again? 5.236 radians per second. So we know how many revolutions this turntable, this record player, is rotating per minute. 50 revolutions in 1 minute. Right? So per second, it's covering 5.236, per second. Per second, it's covering 5.236 radians per second. Okay, well, think about that. 6.28 radians per second would be a full revolution per second. Kind of gives you an idea, back in terms of revolutions, of what that really means. Okay. The next thing we're going to switch to is degrees, minutes, and seconds. But I think I'm going to do that in a second video. I think we're at about 35 minutes now. I think for this first video, that's probably long enough. So far we've covered radian measures. Okay, some reference angles thrown in there, and then arc length and area, and angular speed. And in the next video, we'll talk about degrees, minutes, and seconds.